Hey everyone, when you see one of those amazing humanoid robots walking around, it's so easy to just focus on the gears and the metal, right? The hardware. But today, we're going to go deeper. We're going inside the machine to explore the mind, the digital software that actually brings all that metal to life. So let's get into it and check out the blueprint for a robot's brain. So what is it? What's that secret ingredient that gives a pile of motors and sensors its spark? You know, that thing that lets it move in a coordinated way? Is it just some impossibly complicated mess of code? Well, it turns out the answer is actually way more elegant. And, believe it or not, a lot more like our own biology than you'd probably guess. Really, the best way to wrap your head around it is to think of it as a digital nervous system. I mean, just like our nervous system zips signals from our brain to our arms and legs and brings all that sensory info back, a robot needs pretty much the same kind of framework to function. And that single idea is the key to understanding everything else we're about to cover. And this digital nervous system, it actually has a name. It's the foundation for some of the most advanced robots on the planet, and it's called ROS2. Now, ROS2 stands for Robot Operating System, but don't let the name fool you. It's not an OS like Windows or Mac OS. It's actually what's called middleware. Just think of it like a central switchboard, or maybe air traffic control for the robot. Its whole job is just to make sure that every single part, from its camera eyes to its motor muscles, can all talk to each other, instantly and without any hiccups. It is the absolute glue that holds the entire thing together. All right, so now that we know what this nervous system is called, let's peel back the layers and see how it's built. What are the core components? What are the neurons and synapses, of this digital brain? Okay, so the most basic building block is something called a node. A node is just a small, self-contained program that does one thing, and it does that one thing really well. So you might have one node whose only job is to handle the data coming from a camera. You'd have another node that only controls the elbow joint on the left arm. You can think of them as specialists, tiny little brains, all focused on a single specific task. Okay, so you've got all these little specialists, these mini brains, all humming along doing their own thing. But that's not very useful if the vision specialist can't tell the arm specialist where it needs to move, right? So how do they talk to each other? This is where it gets really clever. The first way they communicate is through something called a topic. And honestly, the best analogy is a radio station. The camera node, for instance, can act as a radio broadcaster. It's constantly publishing what it sees on, let's say, the video feed radio station or topic. Now, any other node in the whole system that needs to see that video can just tune in and become a subscriber. It's a one-to-many broadcast system for a constant flow of information. But what if you don't want to broadcast to everyone? What if you need a specific answer to a very specific question? Well, for that, you've got services. A service is like a direct phone call. One node, we'll call it the client, dials up another node, the server, and makes a request. It might ask, hey, can you calculate the exact path to get from point A to point B? The server does the math and sends the answer directly back to the client that called. It's a direct, one-to-one conversation where you wait for a response. So let's break that down. Topics are like a radio broadcast. You just shout out information continuously and whoever's listening can grab it. It's a fire and forget kind of thing. Services, on the other hand, are like a phone call. You ask a specific question and you wait for a direct answer. Any smart robot is going to need both of these, that constant stream of awareness from topics and the ability to ask for specific help using services. Let's put this into practice. Imagine a robot wants to pick up a cup. Step 1, a camera node is constantly publishing video frames to a camera topic. Step 2, a vision node is subscribed to that topic. It sees the cup and decides it wants to grab it. So it makes a service call to a motion planning node, asking, hey, what's the best way to move the arm to these coordinates? Step 3, the motion planner sends the path back, and the vision node uses that info to tell the arm nodes what to do. See, it's this beautiful, seamless loop of communication. So we've got the nervous system. We get how all the different parts can talk to each other. But how do we, the humans, talk to it? How do we actually write the instructions for all this? We need a bridge, right? We need some way for a programmer to use a language they already know and feel comfortable with to create all these nodes and topics and services without having to learn some crazy new system from the ground up. And that bridge is called RCL-Pi. It's the official library that lets developers write everything for the robot in one of the world's most popular, easy-to-learn languages, Python. And this is an absolute game changer. It means that millions of programmers out there can suddenly take their skills and apply them directly to building advanced robots, which is just incredible. So the whole workflow is just super straightforward. A programmer writes all their logic in Python. RCPy steps in and acts as this perfect translator, turning all those Python commands into signals that the robot's ROS2 nervous system can understand and act on. It really is the universal translator between what a human wants and what the robot does. Okay, we have a brain, we have a nervous system, and we have a way to talk to it. But there is one more critical piece of the puzzle. The brain has to know about the body it's actually living in. I mean, think about it for a second. You can't tell an arm to move if you don't know how long that arm is, or where its joints are, or how far they can bend. The software needs a perfect one-to-one digital map of the physical robot it's controlling. And this is where the URDF comes in. That stands for Unified Robot Description Format. And just like the name says, it is the robot's digital blueprint. It's usually a single file that meticulously describes every single physical detail of the robot, every single link, every joint, every dimension, all so the software knows exactly what it's working with. So what's actually in this blueprint? Well, it details the robot's kinematics. That's just a fancy way of saying how its limbs are connected and how its joints move. It also describes the physical properties of every part, like its weight and how it's balanced. It even includes the visual models, so you can create a perfect 3D simulation of the robot on a computer screen. It's literally the robot's complete digital self-image. So let's just put all the pieces together one last time. You've got ROS2 acting as the central nervous system. You've got nodes, topics, and services as the language it uses to communicate. You've got RCLPy as the translator from our language, Python, to its language. And you've got the URDF as its body map. And when you combine all of that, what do you get? You get a complete, incredibly powerful framework, a system that allows a bunch of metal and wires to actually sense the world around it, think about what it needs to do next, and then act with real purpose in our physical world. That is the mind of a robot. And that, of course, brings us to a final and pretty thrilling question. We now have the fundamental blueprint for a robot's mind. We actually know how to build its nervous system. So the real question isn't how we do it anymore, it's what. What do we teach it to do next?